Module 3, Lesson 4. Why do banks pay you to provide their services? So there are two instructional outcomes here. One is to compare the rate of change for simple and compound interest. So we're going to look at both of those formulas. And then number two, recognize and solve situations in which a quantity grows by a constant percent rate per unit interval. So this will be situational based on different scenarios about money growth and decline and so forth as to what is actually occurring. So there's really two formulas we're going to focus on, and that's one is simple interest, which we see here, and the other one will be the compound interest, which we'll take a look at in a moment. So simple interest is really this piece right here, where they tell us the interest, which is the I sub t is the interest earned, is equal to the P, which is the principal amount, the amount that we started with, the rate, written as a decimal as opposed to a percent, and the T, where time is represented in years. So they tell us in this situation, Kyra has been babysitting since the 6th grade. She has saved $1,000 and wants to open an account at the bank so that she will earn interest on her savings. The simple bank pays simple interest at a rate of 10%. So they want to know how much money will Kyra have after 1 year? What about after 2 years if she does not add any money to her account? And what about 5 years at that point? So if we look at 1 year, how much will she have? Well, again, we're going to use this formula. The I sub t equals P for principal times the R, which is our rate as a decimal, times that given time. So they tell us in the problem that she initially saved $1,000. That's what she's putting in. So $1,000 times her interest rate, which is 10%. So we'll put times 10%, and she's going to leave it there for 1 year. So we'll multiply that by 1. So we'll start by taking that 1,000, multiply that by the 0.10, and then multiplying that by 1, and it turns out that the interest earned, and we'll talk about this in a minute, the interest that her account earns after 1 year based on a 10% rate at $1,000 is $100. Now, that's not what she has in her account. The question says, how much money will Kyra have in her account after 1 year? And so I have to take that 100, I need to add that to the 1,000. So if I want to know the amount in the bank, so we'll just make a note, the amount in the bank, I have to take my original principal, and I have to add that to the $100 that I earned. And so I've got $1,100 in the account. I didn't even write that right. So we will write that correctly. $1,100 in the account. So the question follows says, well, what if she left the money in the account for 2 years and she doesn't add any additional money? So we're talking about the same amount of money that we've already got, the $1,000. So we would have our I sub t equals my $1,000 times my 10%, but I'm going to leave it in there for 2 years. Won't touch the money for 2 years. So the interest that I'm going to have on that, if I multiply the 1,000 times the 0.10 multiplied by the 2, I'm going to end up with $200. Now again, that's not the amount that I have in the bank. To get the amount in the bank, so we'll just say the amount in the bank, I need to take the principal amount, the $1,000 that I have to add the 200, and then so I would end up with $1,200 in the bank. So if I wanted to leave it in there for 5 years in the account, and I wanted to find out how much I would have in the account after 5 years of never touching the money in the bank again, to illustrate the process, I would have I of t equals my 1,000 times my 0.10 times the 5 years I'm going to leave it in the bank, So the ICE of t, or the interest earned in 5 years, would equal $500. I add that to my 1,000, so 1,000 plus my 500, and I get the $1,500 would be in my account, provided that I didn't add or remove anything from that account 5 years later, based on this particular interest rate. Following up example 1, we have another person who says Raul needs $200 to start a snow cone stand for this hot summer. He borrows the money from the bank that charges a 4% simple interest a year. So the question is going to be in part A, how much money will he owe if he waits 1 year to pay it back? If he waits 2 years, and then 3 years, and 4 years, and then 5 years, and so on. So how much will he owe if he waits at that point? So he has initially $200. There's a simple interest of 4%. So we know that ICE of t is equal to the principal amount that we have, that's the $200 that I borrowed, times the 0.04 for my decimal as a percent, and then multiplied by 1 year. So 200 times the 0.04 times that 1 year, the interest on that account will have increased by $8. Now, it doesn't mean he just owes $8 to the bank. That means at this point in time, if he waits 1 year, he owes $208 to the bank. Now, let's say he doesn't pay it back the first year, and he waits 2 years to pay it back based on this information, that I could say ICE of t is equal to 200 times my 0.04, but I'm going to wait 2 years to pay that back. So if that's the case, then my ICE of t is going to equal 200, well, it's going to equal $16. We'll start with that. And that means I will owe $216. If we do it one more time, for 3 years, ICE of t equals 200 plus the 0.04 times the 3 years. And so when I solve my ICE of t, then I'm going to end up with $24. And my ICE of t will equal $224 as I would owe. We could continue the same thing with 4 years and 5 years, but what I want to draw your attention to is the uniqueness of this. We started out owing $200, and then we owed $208, and then $216, and then $224. If you notice about this given pattern, the way that I get from 200 to 208 is that I added 8. If I go from 208 to 216, I added another 8. If I go from 216 to 224, I'm adding 8 again. So while I can continue this process, if I wanted to know what I would have in 4 years, then I could take and I could add 8 to that given value there, and I'm going to end up with 232. And if I wanted to know in 5 years, I can add 8 again, and I can get 240 for that value. Now, why is that important? Why would I bring that association up? Is in part B, they say to write a formula for the amount that he owes after t years, to write a generic formula. So one thing that's interesting to note is if I'm adding by 8 every single time, this is known as an arithmetic sequence. So that comes from what we talked about in lessons 1 and lessons 2, and if you need to go back and review that, I would encourage you to go back to lessons 1 and 2 in this particular module, Module 3, and look at what it means to be arithmetic versus geometric. But if I know that, then I also know that my terms that I'm trying to write is going to be the first term. So a plus my common difference, and then n minus 1, the given term that I'm looking for. So my first term was $200. That's how much I borrowed. The common difference is that I'm adding 8 every single time. And then n, or if you wanted to replace n with t, the number of years, you may. N or t does not matter. T referring to the number of years, first year, second year, third year, fourth year, fifth year, same as n equals 1, 2, 3, 4, 5. It can be left like this, or it can be distributed out to where you would end up with 200 plus 8t minus 8. And so then if I do 200 minus 8, I would end up with 192. So my generic formula would be 8t plus 192. So again, either equation is fine. If you wanted to leave it like this, your teacher will be fine with it like that. Or if you wanted to simplify it so it looked like that, then that would be fine. Both of these given equations would give you this given sequence over here, the 200, 208, 216. And the nice thing about that, again, if I said that I wanted to predict what would he owe if he did not pay the loan back in, say, 20 years, then I could find that out simply by doing 8 times 20 and adding 192. So 8 times 20 is 160. I can add my 192 to that. So 160 plus 192, I would end up owing $352 on that particular loan given this scenario. In example number 2, we show the other interest formula, the compound interest, where notably it is a little bit different than what we saw before. It gives us a symbol called FV, which is known as future value, PV, which is the present value. It's similar to the principal, only thing is it changes after every single year. The rate as a decimal, that doesn't change, and the T represented in years. So it says Jack has $500 to invest. The bank offers an interest rate of 6%. So we have $500 and we have 6%, and it's compounded annually. So they want to know how much money will Jack have after 1 year. So we want to determine what that future value is going to be. What will we have 1 year down the road? So if we know that our present value is $500, the amount that I initially invested into the bank, I would put 1 plus my rate, which is 0.06, and I'm going to raise that to the first power, or in other words, which would represent 1 year. So I could simplify a little bit if I wanted to. I could say 500 times, well, 1 plus 0.06 is just 1.06 if you want to remove that plus, and that's raised to the first power. Anything raised to the first power is itself, so you end up with 500 times 1.06, and if I multiply that together, 500 times 1.06, we're going to get $530. Now, this is where this formula is strikingly different. Remember, we mentioned that the future value is the present value. We'll put the key emphasis on present. So if I left my money in the bank for 2 years, well, after the first year, I have $530 in the bank. So if I want to know my future value, well, the present value is no longer 500. My present value is now 530. This is where it's very different from simple interest. Everything else stays the same, so I've got the 1.06, but this time I raise it to the second power. So when I put that in your calculator, 530 times the 1.06 raised to the second power, and put that in, I'm going to get this value here, I'm going to get $595.51. We'll round that a little bit. And so that's what we would have in the bank after 2 years. So if we want to fast forward 5 years, you continue to figure that out and so forth. But that gives you an idea of what's happening in that given design. For 5 years, just as a note, if we left it in there for 5 years, and you would need to continue to compound this because you would have to do the 3-year and then the 4-year before you can do the 5-year, and figuring out some of that information. And so in 5 years, we would end up with $669.11, and then after 10 years, it would be $895.42, given how that will play out. So in example number 3, they ask us if we have $200 to invest for 10 years, would you rather invest your money in a bank that pays 7% simple interest or 5% interest compounded annually? Is there anything you could change in the problem that would make you change your given answer and so forth? So we'll just look at the comparison of what's going to happen in 10 years for each one. So we'll look at this in a slightly different perspective. For the simple interest, we know that I sub t is equal to the p times the r times the t. So if we have our $200, that's our initial, and we want to have an interest rate, they said, of 7% simple interest, so 0.07, times the time, 10 years, then I can find the interest that is developed on that. So 200 times 0.07 times 10 years, the interest that I get on that is going to be $140. So if I take my 200, which is the initial, and I add my 140, I get $340. Now, if I take the other one and I compound it for 5 years, for 10 years, and I continue to grow at that given amount, well, I can look at it in this perspective. Let's say the future value, which we have, is equal to the present value times the 1 plus the r raised to the t power. So the present value is $200. 1.05, and so if we did for the first year, that would be 200 times the 1.05, that's going to be $210. If I go by this again and say 210 times the 1.05, and we're going to put that at 2 years, so 1.05 squared times 210, I'm going to end up with $231, and let's just call it 53 cents. And that design, and so you would continue and work on in that thought process of an idea. And so ultimately, as we work on and get our answer, we would get $325.78 in that particular piece of soap. The other way to look at that is I could just move forward with that and just type in the $200 times the 1.05 and future cast that 10 years. And so that's going to also give us the $325.78. One thing that is interesting to compare about the two and think about is in this design. In this one, I have to take my interest, I have to add it to my principal. This one is going to initially give you that particular amount just by plugging in the number of years that you want to see. So they ask, is there anything you would change in the problem that would make you change your answer? Would you rather this or that? And so then, at 10 years, of course, yes, I would prefer to have the simple interest versus this one. But what's going to happen is at some point, if you think back to a previous lesson we talked about, this is an arithmetic sequence. So your line's going to be going up at a linear fashion. Now, in this one, this is geometric. And so, yes, your graph is going to grow slow for a while, but at some point, it's going to grow exponentially. So at some point, this particular piece in this bank will be a better piece to have. It all depends on how long you leave your money in the bank. If we're saying 10 years, then yes, we would want to leave it in that given piece. Let's say we just fast forwarded 20 years, and so we plug this in here. We replace this 10 with a 20, so we would have 200 times the 0.07 times 20 years, so 200 times 0.07 times 20. I would end up with $280 for interest. Add that to my initial amount, which is 200, so I would end up with 480. Now, if I change this one out, 200 times the 1.05 raised to the 20th power, so 200 times the 1.05, raise that to the 20th power 20 years into the future, I'm going to end up with $530.66. So again, you could see that at 10 years, the simple interest was better, but if I changed it to 20 years, then the compounded annually one would be the one that I want to go with. And that's not to say 20 is the first year that it gained its popularity over the simple interest. That is just one example to show how that plays out in that design. So in the lesson summary, that's what we kind of talked about, the simple interest. We'll simply note simple interest is known as I sub t equals the p times the r times t, and so forth. Whereas in compound interest, it is calculated as the future value is equal to the present value times the 1 plus the r raised to the t power.